Well, that's good. I will begin with a word of prayer. Dear Father, we thank you for this opportunity we have just to meet together and study your creation. Thank you for these students. Just ask that you bless their work this semester, Lord. In your name I pray. Amen. All right, so most of the good students are here. That's good. If you're not here, you know who you are. Let's see here. I should say a few things about myself. I am James Cook. Most of you know that already. It's spelled like this. Just so we're clear. There you go. My email, I'm not going to write on the board. And see, I have office hours Monday, Wednesday, Thursday, and Friday from 8:55 to 10:30. Actually, 8:55 to 11 on Thursday. I also have an office hour from 10:05 to 11:05 on Tuesday before this class, and also Friday afternoon from 3 to 4:15. My office is DeMoss Hall 3183, which is, close to the physics lab. Most of you know this already because you already had me for Calculus 3, right? This course is considerably different than Calculus 3. I mean, Calculus 3 is this luxurious 5-day-a-week schedule, and I devoted a significant amount of time to harassing you into working on the material. I don't do that in here. If you don't work on it, you just fail. So it's up to you. That's not entirely true. I do have these things called quizzes. If I can. Yeah, so I have, just to give you a quick layout of the course, I have arranged there to be 5 quizzes, right, and 2 tests. The tests are each worth 200 points. Test 1 is October 9th, it's right after fall break. And then test 2 is November 15th, which is right before Thanksgiving break. This is for the best. Having a test after Thanksgiving break is a bad idea because after Thanksgiving break is the season of engineering projects. And no good comes of having a test during this time period because it's a time period where math does not matter. So we will have quiz 5 given and collected during that time period. So I hope you can find some time and energy for this course in that season of engineering projects, but that's it. And then of course there's the final exam. So test 1 and 2, both 200 points. The quizzes are worth 250 points. There's 5 of them. That means 50 points per quiz. And you might say, quizzes make me nervous, but you shouldn't be that nervous because if you really look at them, I say quiz 1 given, quiz 1 collected. What's that mean? They're take home, right? So really my quizzes are your homework. I just call them quizzes, right? But I call them quizzes in part because they're not comprehensive, right? I mean, they test some subset of the material. They won't probably test everything. You do need to do work beyond that. I have posted missions from previous years on the web page along with solutions. Those give you a good bunch of problems to work through. Any questions? The missions, for the most part, have the problems stated and also the solutions. So, in principle, you can look at those without a textbook. It's good if you have a textbook. In fact, I'd like you to have a textbook. In particular, the Nagel, Saff, and Snyder. I think I said this in an announcement, right? So 4th or 5th edition. It doesn't really matter to me. I do want you to have the one that's got the chapter on partial differential equations. So they play games with some of the more recent editions. They don't have that chapter on partial differential equations, which is really unfortunate because the partial differential equations chapter is really nice, and we will cover it at the end of the course. And I threw out the idea, of getting rid of that part of this course to Dr. Medina, and he said, no, I want you to cover that. So I'm going to try to keep it. I mean, we don't do a lot of partial differential equations here, just a few days, enough to get us in trouble, all right? This is not an analysis course, right? So like Calculus 2 is in some sense more serious about convergence and divergence than we are, right? So we're a little bit freewheeling and sort of 19th century, in some sense, mathematicians in here. In other words, we care more about formulas and techniques than we do about domains for the most part. So bad math, good formulas. I am going to try to spend more time this semester talking about why we're doing what we're doing than I have classically, and doing some things that I haven't done before, starting today. Let's see here. Any questions about the organization of the course before I say more? Participation is 50 points. What's that mean? Participation? What on earth is participation?
It means free points.
Oh, that means free points? Oh. I feel like there must be something more to it than that. It can't just be free points. No, could? Attendance points. Attendance points. I guess that must be. That must be doing a good job on the camera.
Oh, yeah.
Yeah. So you are. I don't. There's only 19 students and there's 27 classes, so it's not clear that you've earned your points yet. Let's see here. Wait a minute. Did I say 27 classes? This is fall 2018, so I think we only have 25 classes. We lost a week somehow. Anyway, which is part of the reason I mixed up the schedule, because my traditional schedule wouldn't work in here because we were missing a week. So I thought, meh, let's just do something different this semester since I'm already redoing my schedule. There was a point I was getting to here, and this point you will like. You are allowed one page, not exceeding 8 inches by 11 inches, of notes. 2 sides is fine. Only 2. Only 2. For test 1, test 2, and also the final. All right? So one of the things you should be thinking about as we cover material in here is what do you want on that sheet, right? Like what is it that you don't want to memorize but you want to understand? Those are the kinds of things you should put on the sheet, right? Maybe you have a weakness about integrating sine. You should write down integral of sine equals minus cosine plus constant. I had a friend with this weakness. You guys know Crazy Paul? I've mentioned Crazy Paul in my past classes. This is his principal weakness. He can't remember the integral of sine and cosine. He always flips the sign. But anyway. All right, so I think I've taken attendance. We've talked about my office hours. I've talked to you about what we're doing, when we're doing it. The first sort of graded assignment, modulo, of course, camera work, which I grade very strictly. Just kidding. If you don't want to be in the camera, then don't sit where the camera points, right? Unless you think the back of your head is particularly attractive and you just want to show it off to YouTube, then, by all means. Okay. What's that? Oh, okay. Quiz 1 is given, according to my course planner, on Tuesday, September 11th. So that would be 2 weeks from now. I'll give you the first homework. Does that mean you should not just check out, don't do any work on this class until then? No, it does not mean that. This is not physics lab. You should work on this course. That's right. I say these sorts of things in the hope that Ms. Stromby might, perchance, watch this lecture. Sorry, I pretend to dislike physics lab more than I actually dislike it because it's amusing to me. I just don't care about it. It's not that I don't like it. Anyway, all right, so let's get started. So differential equations. What's differential equations about? So today's lecture, I'm going to talk about curves, calculus, and vector fields. And the reason for this is we need to have sort of a sense of what it is we're after. I could just do what I've done in past semesters, which is just start writing down differential equations and solving them, and/or telling you general terminology, and that's fine. It's worked, but I think this is going to be an interesting path because maybe we'll have better appreciation for what we're doing when we're doing it. All right. So what's a curve? My real question to you, you know what curves are, right? If this is a curve, 2-dimensional, whatever, right? That's a curve. How would you describe that mathematically? I mean, I don't have an equation for it. That's not my point. Here, let me make something that I can actually write the equation for. How about that? That was certainly a curve, right? But I mean, I'd have to like really stop and think a while to come up with an equation that looked like, that had a solution set that looked like that, right? But if I have this curve, it's fairly easy for me to, if I tell you where the center is, say 3, 2, right? And if I tell you it has a radius of, 6, probably you can describe that curve, right? What are the two ways we have to describe the curve? We could describe it, how about this, x minus 3 quantity squared plus y minus 2 quantity squared equals to what? Six? How about 36, I think would be better, right? So this is the equation of a circle, radius 6, right, with center 3, 2. But the thing I'm trying to get at more here is that this is a so-called level curve, right? So in this way of thinking, this is f of x comma y, right? That's the level function. And we're saying that the curve is described as the solution set of some equation. This is one viewpoint. It's a powerful viewpoint, right? This is pretty good for describing curves in what? In two dimensions, right? In 3 dimensions, less fun, right? To describe curves in 3 dimensions with equations, you'd need not one equation, but 2, right? What's an equation in 3 dimensions? It gives you what? A so-called level surface, right? Okay. So that's one way we could describe it. But what's the other way? So this is, again, this is the level curve. So this equals to 36, the level curve perspective. But the other way we could describe it would be parametrically, right? And so there we could do something like what? X equals to, how's it go? What's the parameterization for this circle? Is this circle clockwise or counterclockwise? Exactly. So yes, right. Let's write down the counterclockwise parameterization just for the sake of having a thing to discuss. It will be 3 plus 6 cosine t, right? And y is equal to 2 plus 6 sine t, right? And if we just want to cover the circle once, we need to say, 0 less than or equal to t less than or equal to 2 pi. Of course, I think you can recognize that we made some choices, right? You could change the domain of t. You could speed up the arguments for the sine and cosine. There's all kinds of different things you could do and still parameterize the circle. But there is a parameterization of the circle, right? This is a very different way of describing the circle as opposed to the level curve, right? So we're either saying, and we could put these together, right? So what we really have is r of t is a pair. It's 3 plus 6 cosine t, comma 2 plus 6 sine t. This is a path, right? Which covers, it's covering c, right? Or you could say it's a parameterization of c if you like. So this should be a review. I think it's important for us to remember these terms. All right, so what is the interrelation between a level curve and its parameterization? And I'll just say path because that's easier than writing parameterization, right? So if we have the level curve, we're describing it f of x comma y equals to c, and the path is really, it's t maps to what? R of t. which generically we tend to use x of t, y of t to denote those functions that parameterize the curve. What is the interrelation between this path and the level? What equation connects these two? This is essentially, by definition, to say that that path is a parameterization of the curve defined by the, f equals to c, means that when we evaluate f at r of t, what do we get? If you plug in x equals to 3 plus 6 cosine t and y equals to 2 plus 6 sine t into this, what happens? You get 36, right? So we should get, for this more generic, abstract curve, we should get c, right? So that's how they're related algebraically. Okay? That's about all I have to say about curves and paths for the moment. I just want to remind you that there's these two different ways of looking at a curve in the plane. And in fact, if I was talking about a curve in 3 dimensions, I almost would exclusively use the path viewpoint, right? And there we think about physics, and the path actually being a physical trajectory also, right? Where the thing is at time t. So moving on, what's the calculus here? What is the relation, if we think about differentiation, between the level curve and the path? I mean, what happens if we differentiate this? What's that reveal to us? Differentiate with respect to t. What do we get? d dt of f, oops, not a vector, of r of t equals to what? Well, I'm going to, if you don't mind this small manga-style juxtaposition of calculus, I'm thinking of this going over here now. What's d dt? What, 0 is d dt of the constant, right? So this should be 0. But what else is it? Remember, we have a chain rule, a multivariate chain rule. The multivariate chain rule says that this is really the gradient of the level function evaluated at r of t, dotted with dr dt. This is the chain rule here. If you write it out in gory detail, it's like partial f partial x times dx dt plus partial f partial y times dy dt, right? But I'd really like to look at it in terms of the gradient and dr dt, because what is dr dt to the curve? Both of these things are we've discussed in Calculus 3, and you should know what these are geometrically. What is this? This, in fact, is the gradient vector field, right? Evaluated where? At the point r of t, right? And what's the other thing there? What is dr dt? You guys know this. Come on. It is the velocity. Very good. But geometrically, what is it? What does it do? I mean, it points in what direction? The direction you're going, right? I mean, it's the tangent vector, right? Okay. Sure. All right. Tangent vector. But yes, you're right. It's also the velocity. I mean, if I was to say, I don't know, this. That was sad. Let's try that again. Like that. The velocity of that marker, it pointed along the path which it was going, right? Now the velocity is 0. Now, this being 0, what's this say? This says that the gradient and the velocity are perpendicular, right? And so this gives us the fundamental, if I was to draw a picture, if this is f of r of t, well, let's say, good grief, f of x comma y equal to a constant, right? And if I pick a particular point, and suppose that the origin is here for the sake of my convenience of artistry. Suppose r of t is this vector, right? And in this picture, you can add to that picture what? The gradient vector field, right? Which would look something like this. And you can also add the what? The tangent vector, right? The velocity vector. And which direction would that point? You're like, some of you are like, it goes that way, right? But of course, there's a choice, isn't there? In fact, it's not at all clear that the gradient vector pointed that direction either. I need more information to know which direction the gradient vector points as well. What direction does the gradient vector point? It points in the direction to level up, right? It points in the direction of increasing f. That's what we learned in Calculus 3. So the gradient vector points towards higher level curves of f. And, well, the green, it would depend on the parameterization, whether I have a clockwise or counterclockwise parameterization, right? So for my indicated direction, it would be clockwise parameterization. A clock is a thing that we used to put on walls. It has two hands, and they go in a certain direction. This is still a comment which makes sense to people, but the time is going when we're going to need new terminology. I don't know. Well, apparently there's schools somewhere that are like removing all the analog clocks because it confused the students or something. Like, they forgot what a school is for. I don't know. It's frightening, but true. If I didn't have a wife, I would just not even know what's on Facebook, and I would be free of all these stories. All my Facebook knowledge is like secondhand. So anyway, so there you go. That's the picture. This is the relation between curve and a parameterization, right? Now, let's look at this a different way. So what I've just showed you, now the other thing we talk about is the total differential, right? And I'd like to talk about that for a minute, because there's some really beautiful math here. Right, so df is what? It's partial f, partial x, dx plus partial f, partial y, dy, right? This is the total differential of a function of two variables. What does this have to do with this other story? Well, it's really kind of neat. If you just formally divide by dt, you know what it tells you? This says that df dt is equal to partial f, partial x, dx dt plus partial f, partial y, dy dt, right? And that, by the way, is exactly what I wrote in purple over here in an expanded notation. But this equal to 0, all right, is also telling you the relation of dx dt and dy dt for a parameterization of the level curve. Let me give you an explicit example on what I mean by that. If I have, let's say, x squared, suppose I have x squared minus y squared equals to 10, right? And suppose x and y are functions of time, right? Then, in fact, what you can do is you can just say, well, that's 2x dx minus 2y dy. You can divide by dt, and that's equal to 0. And that shows you that dy dt is equal to, well, what's it equal to? It's equal to 2x over 2y dx dt. And there you go. That's the relation. That's the relation of the rates of change of x and y. I mean, we teach this to you in Calculus 1. We call it related rates. But if we're more honest, what we're doing is we're showing you the relation between a parameterization of a level curve and the equation which defines the level curve. See the 2x and minus 2y there, they're coming from the level curve, and dx dt and dy dt, well, those are the x and y velocities for the path. But this is how they're related, right? Now, this assumes what? We've assumed y is not equal to 0 to make this calculation. This is kind of neat what I'm showing you in the sense that if you didn't even know the multivariate chain rule, right? And if somebody taught you differentials, total differentials, if you just had the gumption to divide by dt, you'd discover the multivariate chain rule just through pure heuristic nonsense, right? So that's some of that 19th century formula stuff I was talking about right there. All right, anyway, enough about, that's curves in calculus. All right, let's talk about vector fields. One other thing, sorry. One final comment. So, if we want to describe the relation between, and this is also a Calculus 1 comment, really. If we have dy dx and we want to describe it in terms of the time derivatives of y, if we also, suppose we have dy dx, we have two different descriptions, right? That's the thing, is we're torn between worlds. We're describing y and x, the relation between y and x without time, right? But we're also describing a parameterization of that same curve. What's the interrelation between these two objects, right? Well, what we teach you in Calculus 1 is to calculate dy dx at a given point. What you do is what? You calculate dy dt, and you do what? You divide by dx dt, right? And that gives you dy dx. If you have a parameterization of a path, you want to find the slope at a given point, you just take the ratio of the y velocity to the x velocity, like so. Assuming what? We do need that dx dt is what? Non-zero, right? Otherwise, you get into cusps and all kinds of fancier stuff that we're not interested in at the moment. All right? So, let's see here. What would this have to do with differential equations? Well, let me give you an example that has to do with this and differential equations. Here's an example. Oh, actually, I should shut up. I should come back to this. The example needs to come back after I've introduced vector fields. So, well, I shouldn't really say introduced. I've reminded you what a vector field is. What is a vector field? The reason I'm having this talk with you guys is that in past semesters, I have taught differential equations, and when I say level curve, you guys look at me like I'm crazy, and I just won't have it. We are going to enter this course knowing what a level curve is, what a path is, what a vector field is, and we're going forward from there. So these are small requests on my part, but I insist. Because ultimately, we're trying to solve differential equations, and the solutions to differential equations are often exactly these things, all right? I mean, the solution to a differential equation might well be a path or a level curve, all right? That's actually what I'm trying to get to the point of explaining. What's a vector field? You should say, what kind of vector field, right? Generically speaking, a vector field is an attachment or an assignment of a vector to each point of some object. Now, we can talk about different kinds of objects, right? You could talk about a curve. You could talk about a surface. or you could talk about a space, right? Vector field along a curve might be something simple like, I don't know, how about the velocity vector field, right? Or you might just say the velocity field along the curve, which is doing what? We're attaching the velocity vector at each point along the curve. That's an example of a vector field. All right? On a surface, what's an interesting vector field on a surface? We talked about in Calculus 3 in lots of depth. I'll draw it for you. You tell me its name. How many arrows should I draw? I don't know. What vector field do I have in mind here for this surface? The what? Yes, the normal. This is the normal vector field, or at least a poor picture of it. Normal vector field to surface, right? And then, of course, we talked about vector fields in space. What's an example of a vector field in space that's important to us? I mean, our physics department has a whole course devoted just to this. What's that? Thermodynamics. Dang it. That would be, like, thermodynamics makes me think of temperature, which is an example of a scalar field. So a scalar field is an attachment of a scalar at each point in space, right? The temperature in this room. If we took the gradient of that scalar field, then that would give us a vector field, which would point in, like, the direction of increasing temperature wherever you went, you know? So that's a good example. I was fishing for this one, something like this. And I can't do it just. I mean, this is the best I can do with this kind of picture. How about this? E is q over 4 pi epsilon naught r squared in the r hat direction, where that's the spherical radius. This is the so-called Coulomb field, right? Electric field. And that guy has a singularity at r equals to 0, right? This is the electric field of a point charge. We learned how to calculate the flux of these sorts of things at the end of Calculus 3, right? The number of lines that cut through a given area according to a certain measure. So these are three rather different kinds of vector fields: curves, surfaces, and of course space itself. And they each have their place, right? So the concept of a vector field it's a pretty general idea. So if we want to visualize vector fields, what do you think we should do? Like, let's just think about, well, we can think about vector fields in either 2 or 3 dimensions. Let's think 2-dimensional just for a second, if you don't mind, because my 3-dimensional picture is not that awesome. I will get out the projector and show you some better. I mean, I have a website I'll share with you. You can actually visualize some decent vector fields. And once we do a calculation, we'll try to look at it in the projector. That's my plan for today. But we need to understand the idea behind what we're doing. So let's just think about 2 dimensions for a second here. 2D vector field. So generically speaking, we tend to use the notation F equals to, depending on which calculus. You had Calculus 3 with, like, Dr. Wang or Dr. Smith. You probably use this notation, right? I would not use this notation. For me, I would write this, P comma Q. It's a vector field. Or some other people, as long as we're going through this litany of unnecessary notation, px hat plus qy hat, there's another popular notation. This is a 2-dimensional vector field, right? Now let's just focus in on a window, right? Here's a little snapshot of it. How would we draw that? How do we draw a vector field, right? Well, there's a few different approaches. Here's one. You just draw some arrows. Maybe you pick a grid of points, and at each point in that grid, you evaluate the vector field and draw that in there. Usually, you don't draw the length to scale because otherwise, there's lots of different conventions and approaches to direct visualization of the vector field like this. But something along the lines of you take a grid of points, You evaluate the vector field, and then some scale factor may or may not indicate the magnitude. All right. Now that's okay. It's not bad, but there's another way we can go here, and let me make my example more interesting. So. You know, and so if you had a picture that looks something like that, you'd start to get a sense that this vector field's like twisting around some kind of center point, right? So it turns out that a really useful way, and physics is full of this stuff, to visualize vector fields is using the concept of what are called integral curves, right? An integral curve. Integral curve to f. What does that mean? What's the definition of integral curve? An integral curve is a curve which reproduces the given vector field as its tangent field. All right, so in other words, it lines up with the vector field along the points where it's defined. Okay? And we use integral curves in physics all the time. We call them field lines, right? So like electromagnetism, you can describe the flux going through a surface by counting the field lines. And we use the density of field lines to illustrate, to describe magnitude. Where there's more field lines, it's stronger. Where the field lines are more spread out, it's weaker. All right? This makes sense because of the particular characteristic of the Coulomb field, which is that the field lines are only created or destroyed at singularities in the field. Anyway, that's a longer story. I'm not really interested at the moment. The field lines here are just lines from the origin, spherically outward, right? But we should try to write an equation. Let's try to write an equation which describes the field lines, right? What's that equation? I said it in words, but can we say it with, you know, my little sister was an English major, and she had a friend who liked to argue with the math major about which was better, English or math, and the English major was trying to get the math major to fess up to the importance of English, and she's like, "Come on, like, what are you thinking? What are you thinking?" Because, you know, what do they want him to say? What are you guys thinking? Pictures? You thinking pictures? No. Sometimes. I think most of us think in words, right? But the math major's like, I think in numbers. It's like anticipating the argument and giving a ridiculous response. I appreciate that method of argumentation. I engage in it myself all the time. So I gave you words. Can we think in equations, though? Like, what's the equation which describes this? If I want to describe this integral curve, let's say that the curve has parameterization R of t. Parameterizes integral curve of a vector field f, provided what? What condition makes this path a parameterization of the integral curve? It might be better for me to say integral path, because really I'm after a path, at least at the moment. So what we want is we take the vector field, right? We plug in the path point, and what's it supposed to be equal to? What would make this path an integral curve for f, the vector field f? Notice this is really different than what we were doing earlier. Now the f has a vector over it. It's a vector field. The start of class, this big F was just a level function, which is an entirely different thing. But you guys are smart, so you're not going to be confused by this duplicitous use of f, right? Not smart. Oh no. You guys are still in the summer, is that it? Summer is still going on for you? You're not really here yet? sometimes feel that way. I know I certainly haven't finished the things I was going to do this summer, so maybe it still is the summer, right? Until I finish those things. It could be summer till Christmas. Let's see here. dr dt, how about that? That's what we want. We want that the vector field lines up with the velocity field to the path, right? That condition is what it means for that path to be the integral curve. What is that condition, though? That condition is exactly what we call a differential. That's an example of what's called the differential equation. It's a relation between the derivatives of the path and the given vector field, right? So one of the reasons we want to study differential equations is to find integral curves. It's actually a pretty important problem, right? Let's look at a specific example, see if we can appreciate this further. Let's look at the vector field. And I'll try to choose a relatively simple one. Let's say, this is about the simplest one I can think of, x and y. This is going to be a really kind of stupid example, but it serves to illustrate the idea. So to find the integral curve, what do we want? We want f of r of t, right, is equal to dr dt. But let me write out what that means. For this example, that means what we're looking for is x comma y is equal to what? ddt of x comma y. So what I'm doing is I'm using x and y as a notation for the function. I don't know, I'm trying to find this x and y functions of time. I don't know what they are yet, right? But how does this work, right? This is dx dt, right? dy dt. And you guys had calculus 3. You know how this works. I mean, see here. You know what time it is? Let's see here. So this is equal to that, right? And that must be equal to that. So what do we actually have to solve? dx dt equal to x and dy dt equals to y. This is actually a system of differential equations, right? There's two of them, right? But not really. I mean, we could solve these one at a time. How would you solve these? You should have learned how to solve this kind of problem back in calculus 2, actually, right? To solve this kind of problem, you can separate variables, right? And separate and integrate, right? Separate, integrate, what do you get? Natural log absolute value of x is equal to t plus c1. Natural log absolute value of y is equal to t plus c2. I should be careful. They should be different constants in principle, right? And think about it. If we're finding the integral curve to this vector field, how many constants should be required to describe where that integral curve is? Think about it. In order to describe which integral curve you're talking about, I mean, you got to pick a point, right? If I just say integral curves to the pictured purple vector field I have on the board, there's tons of them, right? I mean, there's another one out here, right? And that one's based on a different set of initial conditions to the differential equation that I haven't written down. Yeah. Right, yeah, for a two-dimensional problem. For a basically you need 1 point because that fixes, once you have 1 point, it fixes the point on the integral curve, and then you can flow from there. Right. Well, you need 1 point, so how many constants do you need to describe a point? Like you just said, 2 for 2 dimensions, 3 for 3 dimensions. Absolutely. Yeah. Unless there were some sort of unpleasant vector field where you had a point where there was not a unique integral curve defined. Like, is it possible to have more than one integral curve to some vector fields from a given point? Did that happen? Let's hope it doesn't usually happen, right? So those kinds of points would be like a singular point. But you can see in my example that there's some kind of pathological point in the center here where you can't find it depends on what you want to say is a curve. But there's some kind of like center point in here which doesn't, depending on how you want to think of it, I would say it's not really a curve. It's a constant solution anyway. It's just a point. That could happen. But setting aside really weird things, at a typical point, if we give a typical point, then we should be able to find a unique integral curve for a typical vector field. So then, great, solve for x and solve for y, right? So this gives me x is equal to plus or minus e to the c1 e to the t, and y is equal to plus or minus e to the t times e to the c2 e to the t, right? And so if you think about that, shnikes. So if we think about that, then we get what? X equals to, well, okay, so suppose we want the integral curve through, let's say, the point x naught, y naught, right? And we can suppose that time is 0, right? You can start the time for your integral curve to be 0 at the point you're given if you wish. You could start it at time 42 if that floats your boat, but I'm going to make it time 0, right? And so, in other words, x of 0 is supposed to equal to x naught, which is also equal to what? Plus or minus e to the c1 e to the 0, right? And y at time 0 would be y naught by assumption, plus or minus e to the c2 e to the 0. So you can pretty easily see then that, in fact, we get thus what? X of t is x naught e to the t, and y of t equals y naught e to the t, and there you go. That's the parameterization, right? The parameterization to the integral curve of this vector field, and that makes a lot of sense. What is that? If you repackage it, you could repackage it like this, right? That's e to the t times the vector x naught, y naught, yeah? So if we look at the plane, we pick the point, x naught, y naught. What's this do? If I were to draw the integral curve, it doesn't quite get to the origin, and it just goes on and on. It's a ray from the origin like that. To get to the origin, you'd have to let t approach what? T approaching minus infinity goes to the origin. If we let t go to infinity, we go off far, far away. If I was to think about not one point, but all points, you see what we're going to get are just, these are my integral curves, right? And so if I want, and the integral curves describe the geometry of the vector field, right? If you can picture the integral curves, you can picture the vector field. Do you guys see that? Now, what if I didn't want to find a parameterization of the integral curve? What if instead I wanted to find a level curve, like just, or you might say a Cartesian equation for the curve? How would you do that? I mean, given what we've already done, what could you do? If you don't want to have a parameterization, you just want to have y is related to x, what do you do? What did we teach you in Calculus 3? Or what should I have taught you in Calculus 3, but I was in a hurry, so I didn't bother. Maybe I did. I feel like I must have made some of you go to the board and do this. Eliminate time, right? So like, if I wanted to, I could solve both of these for, e to the t is what? It's x over x naught, right? But it's also equal to y over y naught. Therefore, y is equal to y naught over x naught times x. There you go. That's the integral curve as a graph, right? Y equals f of x. Now, the reason I did that is because we just went through we solved the system, right? Is there a way to do this without solving the system? Could we just do it directly? This is method 1. Method 2, which is usually wiser, usually a wiser path, would be, okay, so what we're trying to find is dy dx, right, equals to what? Dy dt over dx dt, right? But, if I go back to this initial expression and expand a bit, maybe this is something I should have done already, but I didn't, sorry about that, is this is really p comma q, right, is equal to dx dt dy dt. You see, so this integral curve condition is really the same as dx dt equals to what? P, and dy dt equals to q. So this is generically, to solve the integral curve, you're solving this system of differential equations, dx dt equals to p, dy dt equals to q. The vector field that I'm giving you is not time dependent. All right, it's a static vector field. That makes the system which I just boxed what's called an autonomous system of differential equations. Now, if you're, I probably have misspelled that. If your vector field had a time dependence, we could still go through this. It just wouldn't be autonomous anymore, and some of the things I'm saying would get more complicated. But check this out. So really, generically speaking, dy dt is what? Dy dt is q, right? And dx dt is what? P, right? So we just have to solve that. What now, for the problem we're considering right now, for this example, what's p? P is equal to x, right? And q is equal to, right? This is my p, this is my q. Find your p's and q's is something people said a long time ago. Let's see here, I think. So that's really y over x here, right? So look, the other way we could look at finding the integral curve is we really just have to solve dy dx is equal to y over x. How would you solve that? Hey, this equation's timeless, right? We've eliminated time at the level of calculus instead of arithmetic or algebra, like in step 1. But again, calculus 2 taught us how we do this. We do dy over y, right? Separate variables is my point. Dx over x, separate, integrate. And then what does that give us? It gives us natural log of the absolute value of y is equal to the natural log of the absolute value of x plus a constant, which then gives us that y is equal to plus or minus e to the c, e to the absolute value of x. Oh, I'm sorry. I think I've absorbed the plus and minus. I can't do math. That's just x. I'm an idiot. So I would just say, okay, so really it's just y equals mx, right? where m is the slope. And I mean, of course, we can figure out that the slope should be y naught over x naught, provided x naught's not what? 0, right? Yeah. I mean, when we adopt y equals f of x, we lose vertical lines, right? That's one of the deficiencies in this viewpoint is it has trouble with vertical things. Afraid of heights, I guess. I don't know. So what have I shown you? I've shown you to find the integral curves to a vector field. That amounts to solving the differential equation, dy dx equals to q over p. Or, if we want to find the path, we have to solve a system of differential equations, like this, dy dx dt equals x, dy dt equals to y, right? Like that. Let's do one more, if I haven't run out of time already. We have till 1, right? So, in terms of differential equations technique, what technique am I using today? The only one we seem to need at the moment is what? Separation of variables, right? That will cease being the case for this example. All right, this was fortunate. All right? This one will not work out so nicely. Suppose we're looking at the vector field f equal to, I don't know, minus y comma x. All right? Then let's try to solve the system of the differential equations which will give us the integral path, right? So we'd like to solve, consider dx dt equals to what? Minus y and dy dt equals to x. To find the integral path, need to solve this guy. Oh, well this is, we can't just separate and integrate now, can we? No, we cannot just separate and integrate here because they're coupled, right? The different dx dt depends on y, and the dy dt depends on x, right? They're intertwingled, to use a technical term which doesn't exist. So there are various strategies here. The one I like is to just plug the second equation into the first, in the sense that this implies that ddt, what's x? X is dy dt, right? And that's equal to minus y. Substituting the second equation into the first. And what's this tell us? Well, we could rewrite that. That says that y prime prime plus y is equal to 0. Well, look at this. To solve this differential equation, it seems like it naturally leads us to looking at a second order differential equation. Who'd have thunk it? How do you solve a second order differential equation? Ah, now this is not a problem of calculus 2 at this university. For the past several years I've taught it. You could teach this in calculus 2. It's not that hard. We'll learn this in a few weeks, how to solve this, all right? You could guess the solution right now, though. What do you think the solution should be? What function can you differentiate twice and add it to itself to get 0? That would be a solution to this differential equation. E to the negative x is a good guess. What happens when we differentiate e to the minus x? We get minus e to the minus x, differentiate again.